So, I want to characterize the transformer in my the vintage transformer in the vintage voltage supply because yeah, up to now I was breadboarding. Yeah, you can't see it in that shot. You see it in the other videos. The breadboarded linear regulator. Yeah, a wee bit blind. But now I really want to characterize what the transformer is capable of. And yeah, you know, maybe that thing from another video. It's kind of a load, an AC capable, almost constant resistant load. It uses halogen light bulbs. I can measure the mains AC voltage going into the transformer, and yeah, I calibrated that old $10 instrument according to my Bryman. So I have to add 1 volt to what it's actually displaying. I'm measuring the output voltage. We could measure the output voltage right now with my old Beckman, which I also calibrated a little bit using my newest Bryman. Yeah, I have also to add a 1/10 of a volt to the display. And the Bryman will hopefully, it's already on, measure the current without blowing up anything. Let's see. Oh yeah, it's measuring current. That's nice. And ooh, okay. Yeah, if you've seen the video, the switches are in the wrong way. Forget it, it's working. Okay, so and using that, I will make a drawing in a second. I will try to characterize the transformer. But before that, I will do a little bit of theory. This is not a general transformer theory video, not at all. I hate transformer theory. Okay, it gives me a headache. But I'll show you enough so you can see what I'm doing wrong when characterizing that transformer. Okay, just a second. So yeah, what is a transformer? A transformer is basically 2 coils. In our case, the secondary coil has less windings with some kind of metal core, magnetic core. Okay, and in an ideal transformer you have a number of turns. Let's say that's N primary. Well, is that big enough? Probably not. And N secondary. And if we say the output voltage for secondary is the input voltage V primary. Did I say V? V is German for V. Please excuse me. And that's divided by the number of turns on the primary times the number of turns on the secondary side. And yeah, and obviously the I primary is the I secondary. Writing around the camera is the I primary and exact the inverse of that. So number of turns primary divided by number of turns secondary. So it basically is the ideal transformer steps up or down the voltage in inverse relation how it's stepping down or up the current. These ideal transformer coils have no inductivity, no inductivity, and they have no resistance. And that's of course bullshit. If we look just at the secondary side, we know, and now we come to the equivalent circuit for transformer, we know that secondary winding, I mean, it's a lot of copper. It's hopefully a big nice copper, but it's still copper, so it has some equivalent resistance. And to make matters worse, it's a lot of windings of copper around some metal core. So of course it has an inductivity. And the same is of course true for the primary winding, which has some resistance, and it's a transformer is the definition of inductivity, and it has some inductivity. But that's not enough. We have losses in the core. I mean, the core is basically metal in constantly changing magnetic fields. So there are currents induced in the core. And since metal is not such a good conductor as, for example, copper, these currents produce heat, and so we have some resistive losses inside the core. And that's the reason why transformer cores are normally built from very, very thin sheets of metal which are isolated to each other to keep these loops of current which are induced to them very small. That's simplifying it a little bit too much. Basically, you make the possible loops of current small so that the voltage induced into that loops, which causes the current, is very small, because the smaller area of the loops fetches only a smaller part of the changing magnetic field. But no transformer theory today. And the core itself, again, I said it's loops of current, and there's a lot of metal, so it has its own inductivity, which is normally, if you look into the books, written as that. So your equivalent circuit of a transformer is basically an ideal transformer with no inductivity and no resistive losses, and you have on your secondary, on your outside, you have an equivalent resistant and an equivalent inductivity. Same is true, of course, for the primary winding. And you have also additional losses and additional inductivity in the core itself. And I'm going to ignore all that. My model, and under some circumstances, which I will not check, it's allowed to simplify that, and I will simply simplify it without checking. I say my transformer looks that. I have an AC voltage source, and I have an equivalent resistance, that's that one, and I have an equivalent inductivity, and that's it. And since I have no way currently to measure the inductivity of something like a transformer, I make it even simpler. Okay, so simple, and now we do wrong. Okay, but yeah, so I say I have my AC voltage source, my ideal AC voltage source, and it has just an equivalent resistance. And when we measure that, that equivalent resistance is of course made up from the resistance here above plus the how is it called? Not equivalent resistance. You know, the XC of that inductivity at exactly 50 Hertz. Because we just put, later on in the test, we put resistive load on it. So yeah, everything will be hopefully fine. Okay, so much for the theory. Now I'm just doodle out what I've done with the instruments. Okay, so my test setup is quite simple. I have AC mains, which should be in Europe here 230 volt effective plus minus 10%. Yeah, that's a fact. And that goes of course into our transformer primary, and we measured that. That was the yellow instrument, my real old shitty one, to the left. And you already saw it didn't show 230 volts, it showed 238 volts, which basically is 239 volts in reality. And then we have a secondary, where we measure the AC voltage across. Okay, so this is volts, and then I have the big red Bryman to the right, which measures the amps, and then I have my big load, which consists of, if you haven't watched the video, okay, I stop. It consists of 10 watt halogen bulbs, which I can switch on and off in different configurations. Okay, that's it. Let's take some measurements and then see if we can calculate that resistance from it. Okay, so we have no load. We have 238, that is 239. And as I said, I'm writing that down. Mains, we have 239. Okay, let it be 239. And we have on our secondary side 23.4. Yeah, correction here. 23.4. Now, something will happen that will surprise nobody if I put now a little bit of load on it. The mains voltage is now, come on, 240. Yeah, it will probably even raise more during the evening when people stop cooking. It's 7 p.m. here. Output is now 23.2. That's not too much, and we're drawing 0.907 amps. Okay, you are aware I just built that kind of load because Christmas is coming. Yeah. Okay, that's better. Let's see what we can calculate from these numbers. Okay, what can we do with all these numbers we measured? So mains in, the effective output voltage, and the effective current. I mean, it was only a resistive load. First of all, we can take the first two numbers and divide them, and then we get the transformation the transformer is actually doing, and this is the output voltage is 1 over 10.21 of the input voltage, and this gives us nominal voltages at 230 volts of 22.5. At 220 volts, that was the old nominal voltage in Germany before Europe came. We had 220 volts, not 230 volts. It would have been, and that was the design point for the power supply, 21.5 volts. And in fact, I said we have 230 volts plus minus 10%, so it can go up to 253 volts, and this would give us 24.8, which is or as low as 207 volts, which would give us 20.3 volts. And yeah, plus minus 10. It's not like 5% resistor. This is where you have minus 2.5% plus 2.5%, so you have a 5% band. You basically have here a 20% band. And if you building a power supply, 20% is quite a lot. So, to the more disappointing things. So each time I measured, I increased the load, I measured the effective output voltage, and also had a look at the main voltage. Because the main voltage is, this is not even 0.5%. We're off. I mean, 240 volts, 10% 24 volts, 1% 2.4 volts, so less than half a percent, and we're measuring not that accurately, so I will not make any adjustment for that variation. But anyway, we have our voltage without any load, and then we have the voltages under load, and of course we can calculate the difference, okay, between between no load voltage and voltages under load. And in our crappy, not very correct equivalent circuit, all this delta V must be burned in the equivalent resistor. And yeah, the rest is simple. The resistance of that equivalent resistor is simply the delta V over the current that is flowing. And that was the delta V I measured, and that is the current that was flowing. Sorry, that was the delta V, that is the current that was flowing, and we get these resistance value 0.221, 0.222, 0.263, 0.284, 0.278. And that spread should not be there. So maybe I'm not measuring wrong, but I mean, we're measuring here the voltage on the last digit, which is always a bad idea on digital instruments, measuring something on the last digit. We measuring here our current with a full 4-digit resolution. So this is again not transformer theory, but in that case, yeah, if you measuring two values with digital instruments and you have one value that's only measured on the last digit, or changes only on the last digit, it might be a good idea to switch the instruments around so you get a better resolution. Okay, let's try that. Sorry, it's getting a long video again. Okay, I switched the instrument, so this is now our amps, and this is our amps, and this is our output voltage. And yeah, I'm jotting everything down. We are at 240 volts. At 4.34. Okay. Let me do the calculations. So, if we do the calculations, this setup yielded much more consistent values. I mean, we still have a spread, and using one good instrument and one crappy one. Well, it's not, the Beckman is not really a crappy one, it's only a really old one. You can still get calibration services for it here in Germany, which I won't because it's expensive. Yeah, but we are here within 10%. Okay, that's okay. Now my first attempt, I was yeah, from 0221 to 0223. That's almost 30%. Nah, not, but yeah, this was a 25% spread. Really, can't believe it. Let me do the calculations. What is the biggest? So this is from 0.221 minus 0.284, okay, divided by 0.221. Yeah, that's wow, 29% spread between the biggest, smallest, and biggest number. And just because I was stupid enough to measure my value that changes only very slightly, that is the output voltage under load, with the instrument with a lower resolution. And yeah, I mean, it says something, if we take the middle, 2.0.25 ohms, but yeah, I wouldn't trust that. Not with a spread of 29% of the values. Instead, we have something here which looks much more realistic, with a 10% spread of the value. And yeah, we can decide on 0.31, okay, 5 ohms, which is yeah, ridiculous, plus minus 10% spread, okay, but that's the order of magnitude. 0.31, 0.32, yeah, you decide, you sum them up and take the average. Also, our transformation changed a little bit, but really this is a minuscule change. Initially we had 10.21 to 1, and now we have 10.26 to 1. That's totally within yeah, what these instruments are capable to do. Yeah, now that we have a working setup, my transformer has a second coil. Yeah, sorry, that's news for you. Videos even getting longer, but yeah, we might short that. So my transformer, and we're back here, actually looks like that. It has a secondary. That's not nice. But again, we will make everything wrong and just take the secondary as an independent voltage source and measure it. Same game as before for your viewing pleasure. Okay, so but probably a little bit accelerated. So the results are in, and okay, this transformer has a transformation of 14.66 to 1. Yeah, and yeah, plus minus several percent. Okay, so yeah, it has definitely lower output voltage compared to the other one. So nominal, yeah, 21, 22 volts, and that one is nominal 15, 16 volts. Yeah, can go lower, can go higher, depending on your mains AC, of course. And the equivalent resistance. And yeah, I measured that twice, and yeah, the internal resistance is of course lower because I know it, you don't, I know it. It's the same copper wire they used, but it's less windings, so it has a lower inductivity and a lower resistance. So yeah, it comes down to, what did they say here, 0.315%, and sorry, that's ohms. So I would put that at 0.225 ohms. And the lower the resistance, the harder it's to measure, especially with, yeah, I only have one really good multimeter, as you saw. One very old, which was very good at its time, but now it isn't, and one absolutely crappy one. I mean, really crappy. Yeah, but that gives us a good idea, at least what I can expect if I put that transformer under load. And let's actually test that, okay? Let's verify that. So my transformer is connected to my breadboarded, well, call it linear regulator, okay? And I'm measuring, hopefully, the output current independently from the built-in instrument, which seems to be more precise. And the AC voltage coming out of my secondary coil. And you see it's at 23.22 with only, yeah, the load on whatever that thing burns, and that should be only 10, 20 milliamperes. And so we should be somewhere here at 23.4 volts, but we're already down to 23.2 volts. Now you can attribute a little bit of that to yeah, bad connections on the breadboard. But anyway, let's put some load on it. And I wonder if I've blown a fuse here. No, I have not blown a fuse. Just a second. Takes it off and put it, after disconnecting it, to the 10 amp DC amp range. That would be helpful, huh? No AC coming out of that thing, hopefully. I mean, a little bit is there, ripple. Hopefully not so much. So, again. So, yeah, we're putting a load on of 0.69 amps, and directly we could have a load of 0.91 amps effective. And yeah, let's put a second one on and go down with the voltage until we hit 0.9. Roughly 0.9. 0.91, perfect. And we have now 22.82 volts. Okay, now it's getting significant. We should have 23.1, but we're only getting out 22.8 volts. What the hell is happening here? Okay, let's go up with the load. Next step we measured was 1.8 amps. We increase the voltage again. 6, 7, 1.8. Come on. I really have to order a good 10 turn pot for the voltage, but they are expensive. So 1.8 amps, 1.8 amps, and we set 22.8 volts, and now 22.4 volts. There are 400 millivolts missing. Okay, 22.3, 300 millivolts missing. Let's go all out. Yeah, my linear regulator will have little trouble, but yeah, is that the best I can do? Yeah, it's currently the best I can do. No! 4.3. 4.4, regulating down 4.3, 3, 5, 3, 3. So that was a maximum we took, and this is significant. 21.5, 21.5, 22.1. So over a half a volt is missing at the same current or even less current drawn. Well, the explanation is simple. As I told you, I explained to you the equivalent circuit of a transformer to prove to you that I'm measuring bullshit in some respect. Yeah, this is still good enough for me. Okay, let me explain. So what we initially measured was the AC voltage directly from the transformer, and we put a resistive load on it. That is, we got a current flow that is greater or smaller or looked like that. And that's perfectly fine for the simplification I choose, that is to ignore that there is an inductivity and just say, okay, that inductivity we add it to the equivalent resistance and say that XL at 50 Hertz, yeah, plus the real resistance of the copper wire. Now, in my power supply, we have the output of the secondary going into a rectifier, and then we have a big ass filter cap, and then we have our load. And a capacitive load on an inductive source, voltage or current, is your worst case scenario. So after our bridge rectifier, everything looks, yeah, and I'm omitting the voltage drop over the diodes. It looks like that. Okay? And everybody will tell you that the voltage across your, if there's a load, the voltage across your filter cap will look like, I'll take another color, something like that. yeah, it wobbles a bit and it's recharged as soon as your AC reaches the point to which it has discharged. And that, of course, is a blunt lie, because your voltage while charging will more look like this. Yeah, you have a loss in your transformer to the load. The whole thing will go into its knees. And it will do so even more, because we are no longer have an inductive and resistive load, but now we have a capacity load. That is the current, yeah, our nice blue curve. The current looks something like that. Nothing, 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 nothing. And then suddenly, yeah, we start charging. We peak. Nothing, nothing, nothing. Peak. Nothing, nothing, nothing. Yeah, and the LT Spice guys can generate you nice curves, or maybe we can do it on the oscilloscope one time. And these fast changes in current, yeah, they are, let's say, poison for the inductivity. Not poison for the inductivity. The inductivity just doesn't like it. Remember, inductivity resists changes in current. So you got that additional voltage drop. And that's exactly what we saw here. But since it was half a volt, or what was it, under... I think I'm maxed out at 4.3 amps. Yeah, I should write that down for... Is that my right call? Okay. About minus 0.5 volts at 4.3 amps. Yeah, I want that for calculations. Yeah, that's one problem in my model, in my too simplified model. But yeah, I can live with half a volt error through the evil inductivity I omitted in my model. If you do a switch mode power supply, or switching pre-regulators of any kind, you have to take that into account. But I don't plan to do that. But there's another problem. Just a second. Okay, now I'm measuring the voltage on the secondary. Where are my numbers? Are these my numbers? Yeah, these are my numbers. And we said, okay, without load 23.4 volts. No, that's the wrong one. Where's my secondary results? Here's my secondary results. 16.3, 16.2. Yeah, good enough. There's no load on the circuit. Okay. And I use the secondary only to generate a little bit of a negative voltage. So a few milliamps, no, my 10, 12 milliamps load on it. So nothing. So, but now I put load on the first primary on my 20 somewhat volt rail. Tap. Oh, you see something? Tap. 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 It's breaking in, but I don't, I mean, I put no load on that secondary. And the voltage breaks in. I only put load on the first secondary. Yeah, and this is why transformer theory gives me a headache. We're back to our textbook transformer model, and I had my two secondaries here, and I have my primary here. And of course, in my model to which I measured, I totally omitted all the primary stuff. But the primary in itself, yeah, the winding in itself has an inductivity and some resistive losses. The core has resistive losses and some inductivity. And if you pull current out through one primary, you bog down your to one secondary, you also bog down your voltage through your, or yeah, on your primary coil. And therefore, if you bog down the voltage here in your primary, you also bog down the voltage here in your secondary. Yeah, headache. We shouldn't end on such a depressing note, should we? Nope, we shouldn't. So maybe this will be too early, but Merry Christmas anyway, from my brand new load, which already does a very good job. My oldest digital multimeter and my newest digital multimeter, and my hopefully at some time fully operational again vintage power source, power supply. Bye.